Welcome back, everybody. Let me get this to properly scale to the screen. There we go. So, um, we left off last time talking about how rational expressions is a polynomial over a polynomial. We were originally dealing with just fractions, but now we can expand that concept to functions instead. So expression over expression, variables over variables. But with the concept to understand that's very, very important is that because numbers are technically polynomials, they're just not very exciting polynomials, like 1/4, which I have up there. All the properties that we knew about fractions should also kind of correspond to rational expressions, things that involve variables, made with a little few caveats here or there, but the general procedure that we learned should still apply. So when it comes to things like simplification, we can cancel common factors vertically. For example, like when we had 4/6, there's a common factor of 2 that can be canceled out. Where things differ is in that statement where it says provided c does not equal 0, which we will typically omit, but we'll talk about what that is in just a moment. So we did this example where it was x squared plus 6x minus 16 over x squared minus 4, and we factored that. And so you don't have to write this, but it doesn't hurt to write it. So we would say provided x minus 2 does not equal 0, which means x cannot equal 2. We're going to talk about that in just a moment. So once we finish these three problems, which I'd like you to do, by the way, I'd like you guys to go ahead and start working on factoring them and canceling any common factors. The new challenge, the abstractification that we've seen now is that instead of it being a nice number where we can we've had enough practice with numbers in our daily life so that we can see what the factors of a number typically are. Any even number, we know it has a multiple of 2. Polynomials now, we can't see the factorization right from the start. So that's why we have to factor. So go ahead and start doing that. I'm going to pause the recording while people work through it, and I will slowly fill in the details. People watching the recording, you should go start working through B, C, and D. Okay, so those are the answers to B, C, and D. First one, I mean, you could just to note, so I waited until the very end when I decided I factored everything to start simplifying, but there's nothing stopping you from canceling early and then moving on like that. There's nothing wrong with that. It's just I like to cancel things all at once. Um, so I waited, and so I canceled out a y, and I canceled out a y minus 4. So that would mean provided y does not equal 0, and provided that y minus 4 does not equal 0, which is why I said y can't equal 4. And then the next one, there's a common factor of 3 in the numerator. And then one thing that students will love to try and do, but as a reminder, we can cancel factors. If things are being multiplied together in a fraction, we can cancel common factors. We cannot cancel terms vertically because they are one piece of the numerator or one piece of the denominator. So a lot of students will sometimes I see this in my calculus students sometimes. They'll want to cancel those 3's, but we can't do that because 3 is a factor of the numerator, but it's a term of the denominator. So we can't cancel them that way. So we leave it as is. And then the next thing, the last one, I did the bottoms up for the numerator. And then I tried to do guess and check for the denominator because I was hoping that something would cancel. And so I know that it's a 3w squared, so there's got to be a 3w and a w, otherwise I can't make a 3w squared. And so I need to figure out two numbers that multiply to -20. But I saw that in my numerator 3w minus 5, so I tried to put in -5 there and then checked what would happen if I put a +4 there, and I got the right answer. And so luckily it cancels, but you can use any method you want to factor, and those things go away. And since I've canceled that, provided that 3w minus 5 does not equal 0, or more simply, w can't equal 5/3. Are there any questions on those? Now, as a note, once again, the green thing that I've written, the provided x, y, w doesn't equal blank, that is usually omitted when we do these problems. But we still need to have a discussion about it. So we'll move on unless there's any questions and talk about the provided c does not equal 0 discussion. Now, if you've looked at my work, you'll notice that every single time, I mean, my calculus students mention it to me all the time, that I am very meticulous. When it comes to writing things, the equal sign, I only use it sparingly. I use it when it truly means that these things are equal. And so when I don't write the provided thing, it kind of hurts my soul a little bit because it's supposed to be there. So you'll notice that I always wrote that these things are equal every single time, specifically with part D. This is equal to this. And it was, let me go ahead and adjust it so we can see the equal sign is equal to that. So what we're saying, since we have an equal sign between these two things, is that these two quantities are the exact same. And you'll notice if you plug in numbers like W equals 0, regardless of what you do, you simplify them and you will always get 3/4. If you plug in 1, you'll get that both sides are 1. If you plug in 1, you'll see that you get 5/5 or some other number over some other number, and it will end up being exactly 1. You could do this for any number other than W equals 5/3. Any number besides 5/3, and these two things are equal to each other. However, as soon as you try and plug in that pesky value, W equals 5/3, let's see what happens. So the left-hand side, what you'll get is okay, so 6 times 5/3 squared minus quantity 5/3 minus 15, all divided by 3 times 5/3 squared minus 7 times 5/3 minus 20. And if you plug that into your calculator, because I don't want you to do that in your head, that's too many fractions to work with at one time. That's annoying. If you plug it into your calculator, you will get 0/0 versus the right side. The right-hand side, if you plug it in, you get 2 times 5/3 plus 3 over 5/3 plus 4. And if you simplify that, or whether it be in your head or in your calculator, you will get 19/17. So the left and the right-hand side gave me two different answers. One thing, so first and foremost, these are not equal. And furthermore, this, does anybody remember what we called this? Dividing by 0. If you have 5 divided by 0, we said that was undefined, and that's correct. 5 divided by 0 is undefined. Negative 30 divided by 0 is undefined. But 0/0 had a special name. Does anyone remember it? It's okay if you don't. We don't really need to worry about it too much until we talk in Calc 2 when we talk about L'Hopital's rule. But it's indeterminate. What makes indeterminate different than undefined is that indeterminate is a statement that says that this is indeterminable. We don't know what this value is until we're given context. There might be ways to figure out what it is. In a specific scenario, there is a way to interpret that value, but as it stands, it's not really an existing value. Because 0/0 could be like infinitely many different things, depending on the situation, as you'll see in Calc 1 if you decide to take it. So the point being is that when we tried to plug in that number, these two things were not equal. So we can't claim that they are actually equal unless we add on the statement that W can't equal 5/3. They equal each other everywhere else, but not at 5/3. That is why we have to have that statement. So what we're getting at here is a concept of a limit which is something you'll study in the first unit of calculus. So what you will eventually say is that the limit of this expression as it approaches 5/3 will equal 19/7. That's what the limit will be, but that's something we will get to later on. But it still does play a role for us once we start talking about removable discontinuities in 1 day's time, or 1 day or 2 days time. Yeah, 1 day's time. Or no, 2 days time, because we'll be talking on Thursday. So there is a importance to this other than just it being a stupid nuance in the statement. We typically don't write it though because it's tedious to write. We have to write provided. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 extra pen strokes right there with provided. And then you have to write x does not equal. So 1, 2, 3, 4, 5. And then at 6+ pen strokes at that point. So that's 16 pen strokes that we're saving ourselves. And it's usually assumed from the context that you can just state that they're equal provided that fact. We all assume it and we stop writing it. So, but it is important to understand that it's there. Next thing is to talk about factoring out, and oh yes, Ben.
How did you know it was 5/3?
So the thing that we canceled out was if we go back up here, we canceled out the 3w minus 5. And so based on the fact that we canceled that to get this to work out, we want to make sure that this factor does not equal 0, this factor here. So we're saying provided there's an additional step. There's an additional step here that says provided 3w minus 5 does not equal 0. So to solve for to not solve for w, because we're trying to not solve for it, but we add 5 divided by 3 to get w can't equal 5/3. Is that okay?
Yeah.
Yeah. All right. Oh, Alita, sorry.
Is that also going to be assumed that most of the fractions that are within a fraction, in this case, that's not going to work out?
Sorry, can you say that again?
So like, let's say that we factor out again and it comes out to, instead of 5/3, it's just another fraction from a different problem. Are we gonna assume that it's also provided that it doesn't equal
That value, yeah.
Okay.
Yeah. Whenever you cancel out a value from something in the denominator, you're going to assume that that thing doesn't equal 0. That factor doesn't equal 0. So one useful fact, as it does show up, it shows its nasty head every once in a while, is the occasion where you need to factor out a -1. So the key fact to remember is that if you have a plus b, if you really wanted to, you could factor out a negative sign from that and make this -a minus b. Similarly, if you had a minus b, you could factor out a -1, and then the a becomes negative and the b becomes positive. So we typically write this as then positive b minus a. So as some examples of this situation, if you had x plus 3, I don't necessarily know why you would want to do it. It all depends on the problem, but maybe you need to factor out a -1 from this, and then it would become negative quantity -x minus 3. Or maybe there's a situation where you have 2 minus 5y. And typically speaking, if it's me, I don't like to see my leading terms, my highest degree terms being negative. So maybe I factor out a -1 here. And if I do that, this becomes negative the quantity 5y minus 2. Because now the 5 is positive and the 2 is negative. So that's why I've written it as positive 5y minus 2. Because I factored out that negative symbol. We can do this in a myriad of ways. It all depends, but just know that when you factor out a negative, it's going to change everything on the inside. And we'll see why that's useful in part A and in part B. So we look at this problem. We've got 4 minus c over c squared minus 4. Now 4 minus c, try and factor it by itself, looking at it just purely as a singular item, there's not really anything to do. It's not a difference of squares because it's not 4 minus c squared. If that was the case, you could factor it, but that's not what's happening here. And there's no GCF to factor out. So let's leave it alone for a second and only work with the denominator. So leave a little bit of space, so leave a little space up above. And so you got 4 minus c divided by c plus 4 times c minus 4. And so as soon as you see CC, as soon as you see your variable and the same number involved, it's a good thought to try and factor out a -1 and see if it's the same thing. As you get better and better at this, you start recognize it right away. I know that the c minus 4 and the 4 minus c will cancel out nicely, but that's only because I've been doing this for so long. I don't expect you to see that off the right off the bat. So instead, try to factor out a -1. It might help, it might not. And it turns out that if I factor out a negative from this thing, I'll get negative. Now I've got a positive c and a -4. So I'll write it as negative the quantity c minus 4. And then, lo and behold, the c minus 4's cancel. But don't forget about that negative sign. It's still around. So this equals -1 divided by c plus 4.
No provided on there?
So, great point. So I should say, and so what I'll say out loud is provided that c does not equal 4. I'll say that out loud that we all understand. Because I've canceled out the c minus 4, technically speaking, these things are only equal as long as c does not equal 4. But we don't really need to write it because it just takes too long to write.
4 or negative?
4. Because we're setting this factor, c minus 4 equal to 0, or to not equal 0, and to solve that equation, you add 4 to both sides. And that's why c can't equal positive 4 and not negative 4. I'd like you to do part B, realizing the fact. So the whole thing is noticing that 4 minus c, it has the exact same numbers as both of these factors. So factoring a -1 might help us. It may help, may not. It did in this case. Sometimes it doesn't. I'm going to pause the recording while people do this one. People watching the recording, you should pause it too and work through it. So you should get this, either x plus 6 over -1, or you could rewrite that because dividing by -1 is the same thing as multiplying by -1. They end up being the same thing. And if you don't believe me, just multiply your expression by -1 over -1. Right? We can do that because that's cleverly multiplying by 1. -1 divided by -1 is 1. So when we multiply by 1, nothing changes. Then -1 times -1, the denominator becomes +1. And dividing by 1 doesn't do anything. So we can just ignore it. And now the negative sign is up top. So that's another way to write it. Or if you really want to, you could divide the -1 into each thing. So x divided by -1 is -x. +6 divided by -1 is -6. So that's another way to write it. Any of those three answers are the same. But the whole thing is I saw a 2 minus x and I saw an x minus 2. They could cancel. Maybe they do, maybe they don't. If this had instead been, just as a small side note, maybe it was x squared, x plus 6. So I don't need to write this down. And maybe it was -x minus 2. And it looks like it should work out, but it doesn't. Because remember, the first one's +x minus 2, and the bottom one is -x minus 2. You can check out, if you factor out a -1, it'll make it very clear why it doesn't work. If you factor out a -1, this now becomes +x plus 2. So these things can't cancel because they're not the same factor. So sometimes it works and it helps you out in your, it helps out a lot. Other times it doesn't. It all depends. But it's a useful trick to keep in mind. Say again? You could factor out a -1 again from the numerator piece, but then it'd be -x plus 2. And so it still wouldn't work out because it's not the exact same factor. So, yes, Cheyenne.
So if it doesn't cancel out, would the answer just be like how do you have it right there?
Exactly. You would just leave it as is, or you could leave it unfactored at all. You could leave it like if nothing simplifies. So if this had been like that, you would just leave it as is because there's nothing to simplify. So good, good. Any other questions? So it's a very, very useful trick to factor out a -1. So keep that in your back pocket. It's one of those things that it's a rare tool that we use in our mathematical toolkit, but it still does get used. It's like a wood clamp, right? You know, if your kid breaks their wooden toy, you can use that thing to keep it held together and fix it. But you're not breaking, like your kid hopefully is not breaking toys all the time. You don't need to use a wood clamp very often, but every once in a while it's helpful. Okay. So, moving on though, as a reminder, rational expressions behave almost exactly like regular fractions with a few extra caveats as we've seen. So, multiplication and division happen roughly the same way. We had this for fractions, now we have it for rational expressions. So instead of saying A, B, C, and D are some numbers, now we're saying they're some quantities. They could have variables, they could just be numbers, they could be a mixture of both. Then, if you have A over B times C over D, that is equal to A times C divided by B times D. So we multiply across. Just like usual. We're not learning anything new. We already knew this. We already knew that to multiply two fractions, you multiply across. It's still true. If there was some new procedure that had to be done, then it would have to work on regular fractions, but that's not how we multiply regular fractions. So division. So if we have A divided by B, so A over B, the fraction, divided by C over D, which could also be written differently. Would be written differently. That's A divided by B over C divided by D, like that, with a big line in the middle denoting the main division bar. Then that is equal to A divided by B times D over C, which is AD over BC. So we flip and multiply. Just like usual. When you divide by a fraction, regardless of whether the fraction is just a number or if it's a variable expression, if it has variables in it, regardless of that, it's always flip and multiply, just like it was before. So we're rewriting it again to remind ourselves of this fact, but this is not new. This is what we already had. So let's go ahead and work through these things, and then reminder how fractions worked. So don't worry, I'm coming right back to this. If you haven't finished writing it, we'll come back to it. But if we go back to 0.3, when we were talking about fractions, and we were talking about fraction multiplication, there was, with part B, you could do it the really long way. You could multiply the numerators together, multiply the denominators together, then start finding common factors and reducing it. But we saw that took a very, very long time to get to the same answer. Instead, it was far more feasible and far faster to cancel vertically and diagonally wherever possible before you went on. So, much like with the simplification that we just did, it behooves us to factor everything before multiplying out. So with this first one, which we'll do together, 5 is just 5. 3x plus 24, there's a common factor of 3 in that. So we can factor that out 3 times, and then that'll be x plus 8 times 9 to x plus 72. 72 is divisible by 9. I can't remember which one. There's that cool trick. 8, yeah, there you go. So it'll be 9 times x plus 8 divided by 8. And I know it's tempting to want to cancel out these like that, but that can't be done. As a reminder, once again, the 8 up here is a term of this factor. X plus 8 is a factor of the numerator, of the second numerator, that is, but it's a term of that factor. 8 is a term of that factor, whereas 8 in the denominator of the second fraction, that's a factor of that denominator. So we can't cancel terms and factors. We can only cancel factors. But we notice that diagonally, this 8 and this x plus 8 and this x plus 8, they can cancel. And then 3 and 9 have a common factor of 3 that can cancel. So let's cancel that out too. We're left with a 3 up top. There's nothing else that can factor and cancel. 5 and 8 don't share any common factors. 3 and 8 don't share any common factors. So up top, we've just got a 3 times a 5, which is 15. And down at the bottom, we just have an 8. So 15/8. And as Hector had suggested, technically speaking, I should say provided that x does not equal -8. So we say that out loud because we all are on the same understanding. We canceled out a factor in the denominator. So we canceled out a situation where we could equal 0. So
If they were right next to, like if you were multiplying them by each other, you wouldn't cancel.
yes, if this x plus 8 was up here, then we would multiply them together. We wouldn't cancel them out because they'd be on the same level. They'd both be in the numerator. So we can only cancel vertically and diagonally. We multiply horizontally. All right. I'd like you guys to do B. And you might notice that right off the bat, you can just cancel the x minus 1s. That's fine if you want to. You can wait till the end or you can do it now. But go ahead and do that. People watching the recording, pause it and do that yourselves. So you should get x plus 2 over 4, or if you want to divide the 4 into each thing, I'll use the pointer to do that. Divide the 4 into x, that's where I get the x plus 4. Divide the 2 by a 4, and you get the 1/2, because 2 divided by 4 is 1/2. And so there was a common factor of x plus 3 that canceled out. And so technically speaking, we should say these things are equal provided that x does not equal -3 from this factor that got canceled, and provided that x does not equal 1 from the blue cancelization. Hector, yes.
For that answer, couldn't you just do 2x over 2?
2x over 2. No, like if it was another x, it would, like they're not like terms, so they can't be combined in the numerator. Is that what you're asking?
Yeah.
Yeah. So if it was x plus 2x, you could combine them, but as it stands, they can't be combined. If it was multiplication, yes. The next one is our first division one, so let's do it together, and then we'll do the big boy problem afterwards. So it's 5x plus 20 over 8x minus 72 divided by x plus 4 over 9 minus x. So we're dividing by a fraction. So we flip and multiply. So this equals, I'm going to go ahead and factor right off the bat. There's a common factor of 5 from the first fraction's numerator. So it's 5 times x plus 4 divided by, the denominator has a common factor of 8. So we'll factor out an 8. And then it's x minus 9 times 9 minus x over x plus 4. We flip the fraction and change it to multiplication. So it originally was divided by x plus 4 over 9 minus x. Now it's multiplied by 9 minus x over x plus 4. It got flipped and multiplied. And the x plus 4s will cancel. Yay. Does anything else cancel? The x minus 9, but we have to see it right. This, if you factor out a negative, now the 9 is negative and the x is positive, so we can write it as positive x minus 9, and there we have it. Now the x minus 9s cancel, but don't forget about your negative sign. If it's me on an exam, I like to bring a highlighter or something or just extra pens and I can circle that. So I remind myself I need to have that minus sign involved. So up top, the only thing that's left, the x plus 4 has been canceled, the x minus 9 has been canceled. All I have is a 5 and a negative 1. So the numerator is -5. The denominator is +8. With once again the assumption that provided that x does not equal 9 or -4. Any questions?
Why?
Why? Why are we doing this? Yes. Yes, absolutely. You should ask why. So, honestly, to be completely transparent, in the real world, there's not really many uses to simplifying rational expressions, unless you see me at your local Magic the Gathering tournament. Not that I'd ever play a draft. I'd never do that. That'd be weird. But if I did, maybe I'd ask you that question there. But otherwise, not going to help us. However, this is necessary information in order to work with bigger concepts. You'll notice that we haven't gone over 1.8 yet. We skipped that section from Unit 1. And that's because one of the things we'll talk about in Unit 1 is combinations of functions. Well, 1.8, we'll talk about the difference quotient, and we'll talk about combinations of functions. And both of those things will end up having fractions within fractions, or more specifically, rational expressions within rational expressions. And we need to know how to work with them. And then more and more importantly, right now, the next section is going to be talking about rational functions. So we need to know how to work with them and how they operate. So that is the reason why we are studying it. So I'd like you guys to do part D yourselves. The main division bar is right in the middle. So we're dividing this quantity by this quantity. So using the flip and multiply, go ahead and start working through that one. I'm pausing the recording. Back to it, you should get this 9 times x minus 2 over 2 times x minus 1. Remember, the 2's can't cancel because one of them is a term of the factor x minus 2, and one of them is a factor. You can't cancel terms and factors. So we leave it as is, provided that x does not equal 3 or x does not equal -3.
You put a multiply, like distribute the 9.
Oh, we could do that. Absolutely.
That's what I got.
Or you could write it as 9x minus 18 over 2x minus 2. Either way is sufficient to me. When I say simplify a rational expression, I mean write it so that nothing else can cancel. As long as nothing else can cancel, you're good. That's my requirement for it, but there's nothing stopping us from distributing in the 9. That would be technically more simplified, but it's fine enough to leave it in either format. All right, and we have a bunch more examples. We got 3 more examples. So I'd like you guys to do A and B yourselves, and then we will come together for C, because C's got a lot going on. So it's good to talk about that one. So go ahead and start working through those ones now. I'll stop the recording, and you should do it too. So here are the answers for these ones. Lots and lots of practice. This is a lot of good practice with factoring and everything like that. That's another reason why I like this section. It's a good practice in practicing your factoring skills. Everything here is practicing factoring. So it's a great tool for helping us stay caught up with the factoring stuff. The main thing that I wanted to mention in part B is, remember, if you're multiplying by an expression, just simple polynomial or something like that, you can always treat it like a fraction, as writing it as 3b plus 18 over 1. So that allows us to actually write this as fraction multiplication, and then we multiply across, and we're able to cancel stuff, and we end up with either 3 times 2b plus 3, or you can simplify it just like I did in the first one by distributing it. And once again, we can't cancel 3 y's in part A, because they are terms of the numerator and denominator, and you can't cancel terms vertically. You can only cancel factors vertically. So the last one is a complicated version of, remember that one problem we were talking about that was like, it's 9 divided by 3 times 2. What is the answer, right? 99% of people can't solve this basic math problem.
Versus.
Yeah. So PEMDAS. Well, or the way I like to see it, PEMDAS, because multiplication and division happen at the exact same time, but left to right. So even though there's a multiplication here, we have to take care of this division first. But oh no, we're dividing by not a fraction. Yes, we are. We can treat anything like a fraction if we want it to. And so we're going to write this as over 1. So that when I do this, I'll flip and multiply. So instead of dividing by negative x minus 6, one second, I'll answer this. I'm really multiplying by 1 over negative x minus 6. Eric, yes.
Does flipping it also flip the multiplication after it?
Excellent question. So no, unless it was combined, in which case it would. Make sure. Yeah, it would flip the whole both of them. Yes. But because of the way it's written, so that's a good point. Parentheses matter a lot. They change everything. So this now becomes, and you can start factoring it right off the bat if you want to, which in the interest of time, this does factor to x plus 6 squared divided by, I'm going to factor out a negative, and I'll get 2x plus 3. Actually, I'm going to just factor that out off right now. Minus 17x minus 30. It's not wrong to keep the negative sign there and factor. It's just for my sanity, I like to see it with a positive coefficient, positive leading coefficient. So I typically avoid that. Then we were dividing by negative x minus 6 over 1. So now we're multiplying by 1 over negative x minus 6. And then the last piece, there's a common factor of 5x between 10x squared and 15x. So I'll factor out a 5x, and I've got 2x minus or plus 3 divided by x squared minus x squared plus 5. That's a sum of squares, not an actual sum of squares, right? Because it's not like 5 isn't a perfect square, but it can be thought of like a perfect like by a sum of squares, and sums of squares are prime. They don't factor over the real numbers. In order to factor that, you have to extend yourself to complex numbers and write that as x plus I squared root 5 times x minus I squared root 5. But we're not going to deal with complex numbers. And then I'm going to write underneath this thing what this is factored to, which is 2x plus 3 times x minus 10. And lo and behold, the 2x plus 3's cancel. And then also the x plus 6 and then the negative x minus 6. They look similar, so I'm going to try and factor out a negative 1 and see if anything happens. And it will. So I factored a negative. So instead of negative x, it's now positive x on the inside. Instead of minus 6, it's now plus 6 on the inside. And that allows us to cancel one of those factors of x plus 6, leaving us with 1 left over, and there is nothing else that can cancel. So up top, oh, don't forget about your negative sign there. Up top, there's one factor of x plus 6 and a factor of 5x. So we get 5x times x plus 6 in the numerator. In the denominator, the negative and the negative will multiply together and give me positive ones. So that's going to go away. And then all I have left is an x plus 10 and an x squared plus 5. And that's as far as we can take it.
You said x plus 10.
I meant to say x minus 10 because that's the factor. Apologies.
What happened to the negative?
There were two negatives. There was, and so we can probably put that as a note. Let's use orange. They cancel each other out. They're not canceling each other, but like with negative ones, they do end up canceling each other out. Negative 1 times negative 1 is positive 1. So, any questions on that? I'd recommend try like basically bringing a piece of paper with you, like tonight, cover up the answer, like the solution that we wrote, and try this problem again. This problem is a very, very good problem at practicing your factoring and your algebra skills with rational expressions. Definitely give some of these problems a try, retry them. I doubt you'll remember them from class today. Like 4 hours from now, it'll look fresh again. So try them again, see what happens. All right, with that in mind, unless there's any questions, we'll take our first break. So people watching recording, go do some guided meditation, something. All right, we're back. And so now we're gonna, oh, go ahead.
You go back to the
Sure. No worries. If you remember, so we've talked about multiplication of rational expressions, but we also need to talk about addition and subtraction. And the reason why we talked about multiplication first is because, once again, much like with regular fractions, in order to add two fractions, they need to have the same whole. They need to have a common denominator. And where it wasn't too terrible to do that with numbers by just looking at multiples of those things, it is much harder to do that with rational expressions because there are many ways to find multiples of polynomials, because you can multiply by x, you can multiply by 1, you can multiply by x minus 6. How do you figure out the common denominator? And the way we want to figure that out is with an interesting pattern. And that has to do with the fundamental theorem of arithmetic. This is kind of the foundation of a lot of things in number theory. And one of those is the fact that every number in existence can be written as a unique product of prime factors. So for example, 12 can be written as 2 squared times 3. 154 is 2 times 7 times 11. That's a product of primes. And you can do this for any number, including obscenely large numbers. 24,696 is 2 cubed times 3 squared times 7 cubed. So you can do this every number. Every number can be written as a product of prime numbers. And so the LCD of any collection of fractions is the product of all the prime factors of the denominators raised to the highest power present, or highest power that you see. So we could do this the old-fashioned way of trying to find the multiples of 72 and the multiples of 42, but that would be a lot more difficult because we'd have to do this a bunch of times. So instead, what we can do is notice that the prime factorization of 72 is 2 cubed times 3 squared, and 42 is 2 times 3 times 7. Really, technically, 7 to the first power. So all the prime factors that we see that are in all of the denominators are a 2, a 3, and a 7. They both share a 2 and 3 in common, but we need to make sure this is a common denominator of all the denominators, so it also has to include a 7. So the LCD of these things would be 2 to the third power. The highest power of 3 present is a 3 squared. And the highest power of 7 present is a first power. And if you multiply those out, you will find out that the LCD of 72 and 42 is 504. So what I wrote here is I had said it has all primes of 72 and 42, but raised to the highest power seen. And so, oh, yes, Ben. So 42 has a 2 to the first power, but 72 has a 2 to the third power. So the LCD, the least common denominator, or the least common multiple, technically speaking, which we'll use to find the LCD, it needs to have at least a 2 to the third power so that 72's 2 to the third can divide into it. So the third power is the highest power seen. The second power is the highest power of 3 seen. And that's why it's 3 squared and not 3 to the first power. The highest power of 7 seen is a 7 to the first power.
are we seeing,
So this time I gave you the prime factorizations. How you would find them normally is you'd probably do a factor tree. So 72, you could break that up into an 8 and a 9. 8 can be broken up into a 2 and a 4, which can be broken up into a 2 and a 2, and 9 can be broken up into a 3 and a 3. So that's why you have 2 cubed and 3 squared. That's how you'd find it if you wanted to find them by hand. I believe your calculators do have the ability to find the prime factorization. I can't remember what the button is, but there should be a way to do it. That being said, this is something that we now use computers to find instead of doing it by hand. And any of the problems in R that we deal with, the numbers will be like the number portions will be nice enough that we don't really need to do that. But this is trying to kind of set the stage on how we find how we find LCDs when it comes to variables. Any other questions? So to show you an obscene example to try and really set the stage, and there was a typo here. This should say 64, not 46. Otherwise, that's not the prime factorization. That's not the writing it as a product of primes. But if I wanted you to add up these things, first and foremost, we should use a calculator because that's just going to be way too obnoxious. But if you wanted to do it by hand, you need to know the prime factorizations of these. So 1,764, not 46, that was a typo, is 2 squared times 3 squared times 7 squared. 6,273 is 3 to the 4th times 7 times 11. And 8,232 is 2 cubed times 3 times 7 cubed. So the LCD should have all the prime factors. So it should have a 2 times a 3 times a 7 times an 11. It has to have all the prime factors. Otherwise, the numbers in question, the original numbers, would not divide into it. If it doesn't have an 11, 6,237 won't divide into it. It has to have an 11. There's no other way around it. In order for it to divide 1764 and 8232, it has to have a 7. Now we look for the highest powers that are present of each of those factors. The highest power of 2 present is a 2 cubed. The highest power of 3 present is a 4th power. The highest power of 7 present is a 7 cubed. And the highest power of 11 present is a 1st power. And so that ends up being 2,444,904. You can imagine trying to do this the old-fashioned way of trying to list out multiples of each number to find out the common one would be obscenely obnoxious. In fact, let me figure out exactly how obnoxious it would need to be in order to find out that the LCD is in fact 2,444,904. It's 244,904 divided by 1764. You'd have to find 1,386 multiples. You'd have to test 1,386 multiples of 1,764 in order to find out what the LCD is. And I don't think that's a very, very feasible way to do this. This is far faster. And hopefully you can see why it works. In order for, so notice, if I make this a 2 right here, then 1,764 goes into it because the 2 squareds will cancel. 2 of the 3s will cancel. 2 of the 7s will cancel, and then it's fine. So 1764 goes into it. But if I made that a 2, now when I try to divide 8,232 by it, it won't be able to cancel out all the factors of 2. That's why it has to be the highest power seen. So if we can think about that and realize that numbers are just very, very basic polynomials, the idea can be abstractified. To find the LCD of a collection of rational expressions, it's the product of all the factors that you see in the denominators, but raised to the highest power observed in all the fractions. So this is an over-the-top example to find out the LCD. So, right, this was not a problem that we want to do by ourselves because trying to add these two things together would be obnoxious. But if it were this case, the LCD of 6 and 8. So 6, as an aside, is 2 times 3, and 8 is 2 cubed. So the LCD, it's technically the LCM of 6 and 8 is going to be 2 cubed times 3, which is 24. That's the smallest number that 6 and 8 go into. So it's going to have a 24. Now, both of them have a factor of x, but the highest power seen is a 20th power, so it has to have an x to the 20th. They both have a common factor of x minus 3, but the highest power present of x minus 3 is the 6th power. Then only the first one has a power of 2x minus 7, so it still has to be present in the LCD in order for it to be able to divide both denominators, or in order to be a factor of both numbers. So a 2x minus 7 to the 18th. They both have an x plus 9, but the highest power seen of x plus 9 is the 44th power. And then they also have an x plus 8. Well, the second one does. And I raise it to the highest power that I see, which is to the 5th power. I know that's a really, really big example, but I'm trying to do it with such obnoxiously large numbers that we see the pattern. Do we need to see another example of this to drive it home? Let's do slightly less extreme to figure it out. So a bonus. The LCD of, let's say, 3 over x plus 2 squared times x minus 3 plus negative 7 over, let's say, x plus 1 times x minus 3 cubed is... There's no number portion for the LCD, so it's just 1. There is a factor of x plus 2 present. So let's write it out. There's going to be an x plus 2 factor. There's going to be an x minus 3 factor, and there's going to be an x plus 1 factor. But then we raise it to the highest powers that we see. The x plus 2, the highest factor that I see is a 2. I'll wait until you've written it down before I continue onwards. I realized I wrote that quickly. I just think this is a really cool fact. And like, this is a very, very good example of how mathematicians really operate. Sometimes we look at simple things, quote unquote, simple things or simpler things to try and generalize an idea. If you've ever heard there's this concept that mathematicians can sometimes visualize the fourth dimension. We can't. It's impossible for us to visualize it. Our poor primitive brains can't handle it. But if you are able to think like a mathematician, you can visualize what would happen. You do what we call projection mapping. You project something onto a 3-dimensional space, which we can understand. So it's a cool concept, but that's what we do. We look at a smaller example to visualize something about a bigger example. And so point being is back to the problem more specifically, it should be x plus 2 squared. Otherwise, it wouldn't. This wouldn't be a multiple of this. There's an x minus 3, but the highest power present is a 3rd power. And then the x plus 1 is raised to the 1st power, so that's it. Any questions on that? Good. So that's how we find them. Factor the denominators, find out all the prime, write down all the factors, the prime factors, technically speaking, and then raise them to the highest power that's present. So This allows us, now that we know how to find common denominators, finding LCDs, we can now talk about how to add and subtract them. So we'll look at this example to drive the point home. So simplify the expression 6 over 4x squared minus x minus 5 plus 2 over 4x squared minus 13x plus 10. So right underneath, I'm going to write their factorizations. This factors to 4x minus 5 times x plus 1. And this factors to 4x minus 5 times x minus 2. Yeah. Now, it would probably take more time to figure that out. We'd probably need to use the AC box method or bottoms up or whatever. But either way, if you do it, you'll find that that's the factorization. So the LCD, the first step, and the reason why the first step is to find the LCD is I cannot add these things in their current format. They are two different wholes. They're variable WHOLES, not a whole as an HOLES, but WHOLES, like a whole, like a cake whole, like a whole cake. So right now they cannot be added because they're not of the same whole. We need to find a common denominator. So we need to find the LCD. That's the reason why that's step one. And it's all the factors present raised to the highest power present. So there's a factor of 4x minus 5. And the highest power present is the first power. There's an x plus 1 present, and it's to the first power, and there's an x minus 2 present. So that's the LCD. That polynomial, 4x minus 5 times x plus 1 times x minus 2. Both the red and the green will divide into that nicely. That's what we're trying to do at the end of the day. Then for each fraction, just like before with numbers, we would multiply each number cleverly by 1 so that we got the common denominator. We're going to cleverly multiply by 1 with the factors of the LCD that are missing from each fraction. That is, multiply the numerator and denominator of that fraction by all factors of the LCD that are missing from it. I forgot what the note was, so just go ahead and like when I was making this, it was like 2 a.m., something like that, and I forgot what I was going to write there. I forgot to finish it, so there's no note. So with the 6 over 4x minus 5 times x plus 1, what is it missing from the LCD? And that's it. Yes, Ben's right. There's only an x minus 2 that's missing. So we'll multiply this by x minus 2 over x minus 2. Plus, the other one was 2 over, in its factored form, 4x minus 5 times x minus 2. What is it missing? It's missing the x plus 1, and that's it. From the LCD, the only thing it's missing is the x plus 1. It already has the 4x minus 5. It already has the x minus 2. So we'll just multiply this one by x plus 1 over x plus 1. The reason we're allowed to do this once again is that we are cleverly multiplying by 1, and multiplying by 1 does not change an expression. If we were to just multiply the denominator by x minus 2 of the first fraction, then we'd be fundamentally changing it because multiplying by something other than 1 changes it. Then we need to remember to distribute. So the 6 goes into those two things and the 2 goes into those two things. And so what we end up with, which I typically don't write, and I'll show you what I mean when we do some more problems, is by doing what we did in green and blue and distributing like we did, we have guaranteed that the denominators are the same. Notice that when I do combine these two things, this has a factor, like the first fraction has a factor of 4x minus 5, x plus 1, and x minus 2. So does the second fraction. It's just jumbled differently. But remember, multiplication is commutative, So we can jumble it however we see fit. So what we're going to see is we've got 6x minus 12 divided by 4x minus 5 times x plus 1 times x minus 2 plus 2x plus 2 divided by 4x minus 5 times x plus 1 times x minus 2. Once again, you might be thinking, but Phil, the second fraction should be 4x minus 5 times x minus 2 times x plus 1, not the other way around. But remember, multiplication is commutative. So it doesn't matter the orientation. A times B is the same thing as B times A. Doesn't matter. So now they have the same whole. I typically skip this step and go to the second one right here. So combine the numerators now. Now that they have the same whole, we're talking about the same type of cake. So we can add the two things in the numerator together. And if we're subtracting, remember that that minus sign, this is where it's different. This is where it's different from normal fraction subtraction and fraction addition, is that when you were doing with fractions, the numerators were only just one object. So if I had 12 over 15 minus 9 over 15, I only needed to distribute the minus sign to one term. But now the numerator has multiple terms, and each of those things needs to be subtracted. So if you're subtracting, make sure to distribute. While leaving the whole, the denominator, unchanged. And in fact, keep it factored. There's a reason why. The reason is sometimes the numerator will have a factor that can cancel. So sometimes when these problems do, which this problem will do, I've already prepped it for this situation. Sometimes when you do that, the numerator will actually have a piece that can be canceled with the denominator. So we want to keep it unfactored, because trying to FOIL that out, it's going to be a lot of work. It's going to be way too annoying because you're going to have to multiply a trinomial by a binomial. It's going to take time that we don't have. We need to spend time with other stuff. So we shouldn't bother doing that. And furthermore, it's just going to hurt us in the long run because we want to see if we can cancel any common factors. So with this one, in this previous situation, these two things are being added. So I'm distributing the adding, but that doesn't really do anything. So it's going to add 2x and add 2 to it. So what's going to end up happening is we've got 6x minus 12 plus 2x plus 2, all divided by 4x minus 5 times x plus 1 times x minus 2. We can do that. And then the last step is to simplify the result where possible. And we may need to factor this, the simplified numerator to see if anything cancels. So if we do that, if we combine the like terms in the numerator, 6x plus 2x, that's 8x. So leave a little bit of space before writing 8x. And then negative 12 plus 2 is minus 10 divided by 4x minus 5 times x plus 1 times x minus 2. Now, if you write this on Alex, it'll probably give you a yellow instead of a red and say, you could simplify this further. And it'll make us annoyed with it because there is a common factor of 2. And if we factor out that 2, you might notice something. We get 4x minus 5. And aha, we can cancel that factor out. So it can be simplified further to a final answer of 2 divided by x plus 1 times x minus 2. which we could FOIL out, but why bother? This is actually more enlightening for us in the long run. Yes, Hector.
Do we have to keep on writing the 4x minus 5, or can we just skip all that and just do the top and then finish at the end?
So if you do that, make sure it's an arrow, not saying equals. Like an arrow that you're taking care of the numerator and simplifying it and then rewrite it again. So yeah, you can skip that, like, and just do that work on the side. That's fine, but I do need to see it. So is this what you're asking? So we have,
The denominator, just hold the place and then do the work on top.
so once you've done this step, you're saying like off on the side, you'll write 6x minus 12 plus 2x plus 2 equals 8x minus 10, and then write this step.
Yeah.
Yes, you can do that. Absolutely. Just make sure you're not saying that these things are equal, because they're not equal. That's just the numerator portion. But you can draw an arrow and say, hey, I'm going to do this calculation so I don't have to rewrite the numerator or the denominator a bunch of times. I'm totally for that. I'm totally for that. It's just, I like to see it in all its glory, because that's just me. Okay. Any questions on that? So don't simplify the denominators. It's unnecessary. You'll waste time.
So when one was doing that, you divided it like 4 to 8. You can do that, right? Like 4 to 8, 4 to 8, 4 to 8, so like 2 and 2. 36 4x minus 5.
Yes, so you can factor out a 2 from the numerator and then cancel it.
What if it doesn't?
If it doesn't, then you're done. So if this had been, let's just say for the sake of an argument, it's not this case, but what if it had been 4x plus 10? Let's just say for the sake of an argument, it ended up being that. You would try and factor out the 2. Sorry, 8x.
So writing just the 4x plus 10, what that is correct.
Yeah, that would be fine.
But it could be
But it can be simplified. You could factor it more, but nothing would end up canceling. So Alex would accept it if you just wrote this.
this is correct, but it could be simplified further.
Yeah, like it will in this one, it can't really be done anymore. You could factor it more, but you can't simplify it anymore. So,
Okay.
all right. So let's go ahead and do some examples. Then we've got 2. So we got that, then that, and that, and we've got, okay, cool. So this one, we'll do this one together. We'll do A and B together, and then I want you to test yourself on C and D. So with part A, we got 5v plus 1 over 7v minus 3v minus 2 over 3v. So what's the LCD? We'll do that off on the side, LCD. For the number portions, they're both prime numbers, 7 and 3. So they don't share any common factors, 7 and 3. So it's 21. It's a multiple of both of them. That's the smallest number that goes both into 7 and into 3. And they already have a factor of v, and the highest power present is just 1. So it's 21v. That's all it is. Just as an experimental situation, if this had been v squared, we'd have to write v squared. Everyone cool with that? So if it had been v squared, if this had been v squared and this had been v cubed, we'd have to write a cubed here, and so on and so forth. But they're both, oh, go ahead.
Multiplying the 7 times 3, it wouldn't change no matter what the multiplicity was.
Yeah, 7 times the 3.
Yeah.
Yeah, because they were both 7 and 3. If it was 7 squared, then you'd have to, the LCD would be 49 times 3. Yeah. So 5v plus 1 over 7v. What is it missing from the LCD? How do we get to an LCD of 21?
You multiply by 3.
Multiply by 3 over 3. Minus 3v minus 2 over 3v. And what is it missing? The 7. So multiply by 7 over 7. So this is where I typically, so what I did going back up, don't worry if you haven't finished it. I typically skip writing this step and go straight to here. I typically skip this and go straight to here, and I'll show you why. By doing what I've done in purple and blue, by multiplying by 3/3 and by 7/7, I have guaranteed that they have the same denominator. They will both have a denominator of 21v. So I can now combine them. And this is going to be 15v plus 3, parentheses, minus 21v minus 14, all divided by 21v. Take a second to make sure you understand where everything came from. Convince yourself of why this is true.
I'm just trying to get the common denominator on this one.
Yes.
Still affecting the numerator.
Yes, and I'll make sure it gets distributed. The 3 in the numerator gets distributed. Ben, yes.
Why are we gonna distribute 3 and the 7 in the numerator? Can't we just leave it in the factor form? So have it in the parentheses of like 5b plus 1 parentheses 3.
So yes, you could write this as 5v plus 1 parentheses times 3, and this as 3v minus 2 times 7. But that's going to end up causing, like, we're going to need to write more steps. It's not wrong to do so. Totally valid. It's just going to end up causing more, like, I'd like you to get faster with your algebra as time goes on. And the more algebra you practice, the faster you get at it. But there's no harm in doing that. Yeah. So that, I'm glad Ben mentioned it because that shows how these things came to be, how they came to fruition. When I distribute the 3 into 5v plus 1, that's where I get the 15v plus 3. When I distribute the 7 into 3v minus 2, 7 times 3v is 21. 7 times negative 2 is minus 14. But these things are being subtracted. That's why I put them in parentheses. Sure, technically speaking, the parentheses around the 15v plus 3 is unnecessary, but I still wanted to do it anyways. And so now this minus sign gets distributed. And so I could either do it all in one step, or I can take steps 15v plus 3 minus 21v plus 14, all divided by 21v. And that will give me 15v minus 21v, that's negative 6v. 3 plus 14, that's 17 over 21v. And there's nothing else that can really be done. 6 and 17 have no common factors. They don't have a v in common. So there's nothing to factor out of the numerator to cancel anywhere. Maybe if this had been a 12, then I could factor out a 6 and there would be something to cancel, but because there'd be a common factor of 3 that could cancel with the numerator and the denominator. But as it stands, there's nothing left to do. And that is our answer.
Where'd you say you skipped?
I skipped writing this. So the step that I skipped is right here, where I write this as 15v plus 3 over 21v minus 21v minus 14 over 21v. I skipped that step because I already knew by multiplying by what I did in purple and blue that I would get 21v as the denominator. It's not wrong to write that additional step. By no means do you need to skip it. It's just, it's practicing getting faster with our algebra. So that's what I'm going to typically do in the future. I'm going to skip writing that, okay?
No.
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 I realize that I say okay with my son too often as a question when I'm like, no, this isn't the, I'm saying okay, but it's a demand. It's not a question, my dude. Or you don't have the right to say no. He's very, very clever, and he is very, very willing to try and test boundaries.
Look,
Sometimes just
People's elbow.
you will do what I say. I'm just asking you to put on your shoes.
because
That's all I'm asking.
he's learning his emotions and personality.
Exactly. He's having big feelings and he's having questions about authority and his autonomy. And so I get that. Some days just wanna I'm kidding. I'm kidding, of course. I'm kidding. I love that kid to death. He's adorable, but he just needs to, we just need to work on our
You're
communication.
5 years old.
Yes. Anyways, I'm joking. Truly, honestly, I'm not, it's not what I'm about. But anyways, this one, the LCDs, they're already factored. Good day. Good. We don't have to worry about factoring at all. So we will now figure out what the LCD is. What's the LCD here? Not 6, but x minus 6, because that's one of the factors. And the other factor that's present is an x minus 2. If it was 6x, then then an LCD would be 6. But it's not. It's x minus 6. That is a factor in itself.
Would it? Right.
No, go ahead.
You just multiply it by 3 and then that's how you would get the least common.
So I'm glad you asked that, because what would happen if we multiplied by 3? If I multiplied this by 3 over 3, then this would be 3x plus 12. That's not a problem, but the denominator would now be 3x minus 6. It wouldn't line up. So it wouldn't be able to be added together. Because that 3 has to get distributed to both things. If it could only get distributed to the 2, it would be great. But that's sadly not how it works. So now that we know what the LCD is, I'd like you guys to start working on simplifying this, knowing that you're going to have to do some multiplication. You're going to have to do some foiling. So I'll pause the recording. People watching the recording, you should do it right now. Pause the recording and do it. Okay, so we should get this. And so what we needed to do is we needed to multiply the first fraction by what it's missing from the LCD, which would be x minus 2, and multiply the second fraction by what it's missing from the LCD, which is x minus 6. We're doing it cleverly. We're multiplying by 1 so we don't change the expression. And then what I would recommend is either on some scratch paper or up above of it to do the foiling, because we need to multiply these two things together. The reason why I'm not multiplying the denominators together is because I want to make sure that to see if there's anything that can factor and cancel. And there, at the end of the day, there won't be, but if we multiply these things together, we get x squared plus 7x minus 18 and x squared minus 2x minus 24. And these two things are being added together, so there's no need to worry about distribution. They'll keep their same signs. But if this had been a minus here, we need to distribute that in. But either way, so we get x squared plus 7x minus 18 plus x squared minus 2x minus 24. Those things are all being added together. You can combine them, and it gives you 2x squared plus 5x minus 42 in the numerator, which does factor. We should always try and factor to see if anything cancels. Otherwise, Alex will give us that, you can simplify it further. With a goofy voice. Right, that's good old. I'm pretty good at my goofy, right?
Gosh, Bill. Oh, man. I think I teach you.
Or you do Mickey Mouse too, maybe. Either way, you should try and factor it. If it factors and cancels, awesome. If it doesn't, it doesn't. And this one, nothing factors, nothing cancels, because this is an x plus 6 and that's an x minus 6. They don't cancel. So we could leave it either in this format, or you could factor it. Either way is fine. I would recommend personally, and I have reason for this later on, to try and leave it in its factored format because of what's going to happen in math in unit 2.5. Because the numerator factor gives us information and the denominator in its factored form gives us information. So we'll talk about that once we get to unit 2.5. The next one and the next two, I'd like you guys to do them. What I'm going to do is talk about part C for just a second before we start working on it. What's the LCD? 5n plus 7, that's right. Because 2 can be considered as 2 over 1. So the LCD here is just 5n plus 7. So go ahead and work through those two. I'll pause the recording so that you should too, so that you can work through it. Okay, so here's the work on both of them. The part C was a lot faster than part D, but so we only needed to multiply the second fraction, quote unquote fraction, it's 2, but you treat it as a fraction, by the LCD because the first fraction already had the LCD. So we multiply 2 by 5n plus 7 or 5n plus 7, and it's being subtracted, so you need to distribute that minus sign. Now, I've had plenty of students distribute the 2 and the minus sign right from the start, so that they'll treat this as a -2 and they'll distribute that in, so they don't have to rewrite another step. That's fine too. Once you distribute the minus sign, you get -7m minus 10 over 5m plus 7. And -7m minus 10 has no common factors. Sure, you could factor out a -1, but it wouldn't really do anything. So that's all you need to do. Part D, we need to know the factorizations of the denominators, which are a minus 2 times a minus 3 and a minus 2 times a minus 4. So the LCD is the culmination of all the different factors raised to the highest powers that we see. So in this case, that would be a minus 2 times a minus 3 times a minus 4. Then, to get them to have the same whole, we need to multiply them by what they're missing. Cleverly multiplying by what they're missing. The first fraction is missing an a minus 4. The second fraction is missing an a minus 3. So you multiply those two like I've done in red and blue, or blue and red, respectively. And I decided to do it above or on some scratch paper, foiling this out. You get 3a squared minus 20a plus 32, and then you get an a squared minus an a minus 6. So combining those things, luckily it was added, so we didn't need to distribute a minus sign. You get 4a squared minus 21a plus 26 over your denominator. And that does factor, and it factors nicely to a minus 2 times 4a minus 13. And so you can cancel out that factor of a minus 2, giving us our final answer of 4a minus 13 over a minus 3 over a times a minus 4. Whew. All right. Any questions on that? Otherwise, we'll take our next break. We'll come back at 11:52. People watching the recording do some push-ups and some sit-ups. I don't know. Sidetrack. We're back. We're back. I got a little bit sidetracked, but okay. So we have 2 more sections to deal with in this thing. It's been a big day. We've done a lot of stuff about rational expressions because there's a lot to them. So the next thing we're going to talk about is how to solve rational equations. Like, look at this one here. 5 over u minus 3 plus u over u minus 2 equals negative the quantity 2 over u squared minus 5u plus 6. So, if we were given that without any context, how would we solve it? And what I want you to remember is, once again, fractions are technically rational expressions. And how do we solve an equation that dealt with fractions? What do we do here? Because we could do it and divide x plus 9 by 3 and break it down into all nice, neat pieces, and then break it down. And we could use fractions because we have calculators, but there was a nice way to do it without having to rely on a calculator. You remember what it was? The answer was to multiply by the LCD. The LCD of 3, 8, and 6, the smallest number that goes into all of those things is 24. So multiply the LCD to cancel the fractions. If I multiply both sides of this equation by 24, when I distribute it into the left-hand side, the nice thing is that the LCD has all of the denominators in it. 24 is 3 times 8. So it will work with the 1/3, it'll work with the 1/8. 24 is also 6 times 4, so it will cancel all of the fractions. So when I distribute it into the first one, I'll get 8 times x plus 9 minus 3 equals 4 times 2x plus 1. Hopefully we all see that, what happened. When I distribute the 24 into the x plus 9 over 3, the 3 cancels with the 24 a little bit, leaving an 8. When I distribute into the 1/8, the 8 and the 24 cancel, leaving me with just a 3 times the 1, which is 3. And then on the right-hand side, the 6 cancels the 24 a little bit, leaving a 4 left over times 2x minus 1. And that is a far nicer equation to deal with, because it's just integers. That's how we solved it nicely. We got rid of the fractions by multiplying by the LCD, because the LCD has all of the denominator pieces present. So that's what we're going to do in this thing. It's the same concept, but we're now abstractifying it, just one level more of abstractification. So solve this thing. First, determine the LCD of all the expressions present. Now, luckily on the left-hand side, these things are already factored. There's nothing else to do, but this one does need to be factored. So we'll write that underneath it. This is u minus 3 times u minus 2. Thank goodness, because otherwise there'd be a lot more to multiply by. But the LCD of these things is u minus 3 times u minus 2. Those are all the factors present. Oh, u, not x. Those are all the factors present, u minus 3 and a u minus 2, raised to the highest power that I see, which is the first power. That's all it is. Maybe, as an aside, if this had been u minus 3 cubed, then there would have to be a cube here. But that's not the case. It's just u to the first, u minus 3 to the first power and u minus 2 to the first power. Then, just like with the fractions, now that we found the LCD, we're going to multiply both sides by that expression, by the LCD. And this will, as long as you've done it correctly, as long as you found the correct LCD, this will wipe out all denominators and leave you with a polynomial equation. And we know how to solve polynomial equations. So let's do that. So rewrite the whole expression. So 5 over u minus 3, and leave some space to the left of it, plus u over u minus 2 equals, leave some space, a decent amount, and then write the negative 2 over u minus 3 times u minus 2. So it should look like that on your paper right now. And now I'm going to multiply both sides of the expression, because remember what we learned about equations is in order to keep it balanced, you have to multiply both sides by the same thing. And I know you're probably, maybe some of you are like saying, well, you told me we couldn't multiply by variables, and we'll talk about that in the paragraph below. So we multiply both sides by u minus 3 times u minus 2. That. And because the left-hand side is two terms, it's the first fraction plus the second fraction, that LCD in red has to get distributed into each of them. But when I distribute it into the first piece, the 5 over u minus 3, the u minus 3's will cancel. So all that will be left is a 5 times a u minus 2. When I distribute it into the second fraction, the u minus 2's will cancel. So I'll still have that u in the numerator times a u minus 3. And then on the right-hand side, the u minus 3 and the u minus 2 will cancel. So the entire denominator goes away, and all we're left with is a negative 2. And like the whole pieces cancel. And that is a polynomial equation. Ben, yes.
Why do we not have the u minus 2 and the u minus 3?
On the left-hand side?
No, in the denominator. So we're doing both on the top. Why aren't we also doing it to the bottom? So yeah, the u minus 3 will cancel out, but it doesn't the u minus 2.
So if we were trying to combine them, we would do that. We would multiply by the LCDs to do that. And that is another way to do it that is also completely valid. So what Ben is suggesting is absolutely another option to do. So you've got that 5 over u minus 3. You could multiply that by u minus 2 over u minus 2. And then you've got the plus u over u minus 2. You could multiply that by u minus 3 over u minus 3. The other side already has the LCD, so there's nothing to multiply it by. And then you can bring everything to one side like you do with a polynomial equation and combine it. This just skips a middleman. It makes it so you don't have to write the denominators every single time.
Oh, I see. So we're doing it u minus 3, u minus 2 over 1.
Yes, and we're multiplying both sides, which is keeping the equation balanced.
Gotcha.
So That is a polynomial equation, which we'll solve in a second. Did I solve it here? No. Okay. Okay. So the thing is, I told you guys way back in 0.3 when we solved equations that you can only multiply or divide both sides by a number, a non-zero number. You can, in certain circumstances, multiply by variables, but we have to be careful with that because variables can be zero, right? A variable, if we plug in u equals 2 for the red, then you're multiplying by 0. That's a problem. But so long as we're not doing that, it's fine. Because if u ends up being 7, what's going on? That is, I don't like this. Apparently now I'm recording a workout too on my watch. Okay, great. But either way, where was I? If it ends up being that when we solve this, we get u equals 7, then u minus 3 times u minus 2 won't be 0, and that's not a problem. So, since we have multiplied both sides by an expression, we have slightly changed the equation, just a little bit, because u could be 0, like u minus 3 could be 0. But as long as we keep in mind that the original equation cannot have 2 or 3 being plugged in, right? Those would make us divide by 0. If we plug in u equals 3, this becomes 5 over 0. It becomes undefined. If we plug in 2, this becomes 2 over 0, and it's undefined. And the other side is also undefined, so it's a problem. So as long as u does not end up being one of those two numbers, it should work out. So that is to say, if when we solve this equation, we get u equals 2 or 3 as a solution, we have to exclude that from the solution set because that is actually not a real value that solves it. It's a what we call an extraneous solution. I like to call them mirages. Like in an oasis, right? When you see an oasis, in the desert, it looks like it's there, but it's not actually there. That's what these are. They're mirages. They look like they actually solve it, but they don't. Yes, so step 3 is to solve the resulting polynomial equation and be sure to check your answers in the original equation to watch out for extraneous solutions. As long as you keep in mind what the extraneous, like the problem values are, in this case, 2 and 3. In this case, it would be 2, 3, and 4. If it was an equation, it's not an equation, but if it was, like maybe it equaled 7 or whatever. This one, -7/5. This one, 6 and 2. This one, just 0. As long as we keep those values in our mind as values that cannot be plugged in, we're pretty fine. So let's see that in action. So we have 5u minus 2 times, plus u times u minus 3 equals -2. Let's distribute that 5 and that u. We get 5u minus 10 plus u squared minus 3u equals -2. And that's a polynomial equation. We can solve, with the way we solve polynomial equations is we bring everything to one side and then factor and cancel or whatever. So u squared plus 2u minus 8 equals 0. 5u minus 3u is 2u, -10, and I'll have to add 2 to both sides to cancel it on the right-hand side. That's why I get the -8. And that factors nicely to u minus 2 times u plus 4 equals 0. And by the zero product rule, now, like the reason why we did this, by the way, is we have the zero product rule, which allows us to write the left-hand side as a product equaling 0, so that one of the factors must equal 0. So we get the solutions, the possible solutions. U equals 2 and -4. However, this is not possible because this can't be plugged into original equation. So the answer is u equals -4 only. Any questions on that? So once again, so now that you've written it down, so we got two solutions, but u equals 2. If you look back to the original equation, try and plug it in. Don't worry, I'll come right back. But if you try and plug in 2, 5 over 2 minus 3, that's -5. No problems. But 2 over 0, that doesn't exist. So how can you have doesn't exist equals doesn't exist? That doesn't really make any sense. That's not a quantifiable value. Doesn't exist is not a value, so we can't make a true statement. So despite the fact that it was a solution, it's not actually a solution because it ends up causing problems right here. If u equals 2, then I'm multiplying by 0 right here and right here. And remember, we cannot multiply by 0. That just wipes out the entire equation. It makes the equation disappear, right? If you multiply both sides by 0, it just goes away. Both sides go to 0. So let's go ahead and see this in action, unless there's any questions. Oh, sorry, I didn't let you guys finish it. And then, of course, there's the SpongeBob meme, right? Check your work. I'm dreading the day where that's no longer relevant. I love that picture too much. But okay. So bottom one. -2 over y minus 4 equals -6 over 3y minus 12 plus 2. First and foremost, I need to find the LCD. The way I think about it is, man, I don't like dealing with fractions unless I absolutely have to. So maybe if I multiply by the LCD, all the fractions go away. So first and foremost, let's write what this is factored underneath it. Y minus 4, that's already factored, that's already done. But 3 minus y minus 12, that is 3 times y minus 4. So the LCD is 3 times y minus 4. Because we need all the factors of the denominators present. One denominator has a 3 present, so 3 has to be part of the LCD. 2 of them have a y minus 4, so y minus 4 needs to be part of it. And that's it. 2 is technically 2 over 1, so it doesn't add anything to the LCD. So we will multiply both sides by that value. So 3 times y minus 4 on the left-hand side equals 3 times y minus 4 of the right-hand side. I said right-hand, I meant the left-hand side. So -2 over y minus 4. And then this one, -6 over 3 times y minus 4 plus 2. Like that. We get out at 12:20, right? Okay, so after this one, we'll call it good so I can hand back the exams and everything. So what will the left-hand side be now? Once I multiply what I've done in red, the y minus 4s will cancel. I'll still have the 3 left over times the -2. That'll be -6. On the right-hand side, I have to distribute this. When I distribute it into the first term, the 3s will cancel, the y minus 4s will cancel, so I'll just get -6. And when I distribute it into the 2, I will get plus 6 times y minus 4. So let's go, and that's a polynomial equation. In particular, it's a linear equation because there's only one power. The power of y is only the first power. So this is going to be solved like a linear equation, but let's go ahead and do that. We get -6 equals -6 plus 6y minus 24. I will get -6 equals 6y minus 30. At which point I'll add 30 to both sides and get 24 equals 6y, which gives me y equals 4. That's a possible solution because I multiplied the equation by a variable. And that variable could be 0. Can I plug in 4 into the original equation?
No.
Nope, I cannot. This cannot be plugged into the original equation. Hope everyone's okay with me writing OGEQ to mean original equation. So 4 was the only solution that I got that was possible, and it didn't work. So there is no solution. By the way, if you ever, going back to that previous one where I said u equals -4 only, as you'll see up above, if you ever see that on my answer keys for things, that means that there were additional answers, but that was the only one that worked. So if there's problems on the exam review for exam 2 that say like blank only, that means that there were possible more, but that was the only one that worked. So if you don't get the if you get that and you're checking work, that should be the answer, yes.
Quick question for where the red is.
Mhm.
How do you multiply the 3 with parentheses y minus 4 into the negative, so the y minus 4, then you get that -6.
So when I do this on the left-hand side, the y minus 4s will cancel. And so this 3 is still left and this -2 is still left. And they're on the same level because this is technically over 1. So when we multiply across, the denominator is all gone. There's no denominators anymore. It's just 1s. But up top, there's a 3 and a -2, which gives me -6. Is that okay?
Yeah, I just thought that the 3 would somehow still be at the bottom.
No, because it's over 1. Yeah. All right. So that'll do it for today. We'll finish off next time with other ones. By the way, if you want to try and solve this one on your own, this is u equals 4. So you can check that. Meanwhile, I'm going to pass back the exams. I'm going to actually bring up the projector screen. If you want to know, I realize I didn't mention this before, but I've got it up on the screen. If you want to know how much you can get on your redo, this is the formula that you can use. X is your original score, plus 100 minus X, that's how many points you missed, divided by 2, that's 50% of them. And that will get you what your potential score could be. So I'm going to pass those out. And Andrew Hanson's not here.
So we can never fully earn back the whole box.
No.
That's like natural tax.
Yeah.
Variable tax. Then.
Julian.
I'm actually going to ask you what's happening. Something different. It's part of this, you just.
Listen. I should probably end the recording. If you guys have any questions, feel free to email me. So these exam redos are due next Tuesday.